something that indeed. So I want to talk tonight a little bit about the history of the universe, especially connections between inner space and outer space. Here's what I am going to do, I think. I'll talk a little bit about the laboratory that I've been at in one way or another for just about 50 years. Move from that to what amounts to a timeline of the history of the universe from over the last 13.5 billion years or so. That'll be the main part of it. Some of the experimental observations that fed into the timeline and the view of that history, I'll make a passing reference to, and I'll at the end try to write down some of the things that are really continue to be mysteries.
Recording is stopped.
So I work at a place in just outside of Chicago, about 40 miles west. One of the Department of Energy National Laboratories. It is a laboratory that concentrates on particle physics and accelerator science. There's about 10 science labs in the Department of Energy portfolio. Most are multi-program labs where they have chemistry departments, biology departments, nuclear physics, and the like. This one is pretty much concentrated on high energy elementary particle physics. It operates the largest particle accelerator complex in the country. About 2,000 people on 6,800 acres of federal land. The 2,000 people, there's probably about 300 physicists, about that many engineers, maybe a few more technicians, and about another couple hundred computer professionals. It's a big site. We've got our own fire department and the like. Typically, we do experiments with facilities on site, but we also collaborate at dozens of other places around the world. It's very much an international endeavor. Each of the experiments, there's more than 50 countries that will participate in a typical year in one way or another, and 4,000 users use it. The lab itself is about 55 or 60 years old, and that's the main building. Here's an aerial view of the complex. The two big features on there are these large circular above ground support facilities for underground accelerators that are at the place. The biggest one in the back was formerly the most energetic atom smasher in the world until about 2012, and it was retired in lieu of the CERN Large Hadron Collider in Switzerland, which we are big collaborators with to this day. The accelerator in the foreground, actually it runs to supply beams for a variety of experiments around the site. So the questions we're trying to answer at this lab are: what are we made of? How did the universe begin? What secrets do the smallest particles hold? And how do they all sort of tie together to help understand what is all about matter, energy, space, and time? So before I get into it too much more, I want to just remind us of a few things that everybody in here probably in one way or another already knows. I'm going to go through these sort of one slide at a time, and then I'll get into that timeline that I told you was going to be the main goal here. Surprising thing is that you go outside at night, and here, there's a lot of stars. It's just great, right? But in fact, most of the sky is dark at night. And what that tells us about the universe, actually, if you do a little bit of trigonometry and head scratching for a while, is that the universe is not static and infinite. It's not both of those things. If it was, it would be daylight all the time. And so that in and of itself, people figured that out back in the 1700s. About 100 years ago, Edwin Hubble was doing his uh, observations in Mount Wilson in California, and he was probably one of the first, maybe the first, to realize that there's more than just the Milky Way galaxy, that there's other galaxies all out there. And more to the point, he also was able to be the first to observe that these galaxies that are far away are actually receding faster and faster and getting farther and farther away. And I'll talk a little more about that later on. Another one of these things about the universe is pretty much there's no special place in the universe. Okay, they're on large scales. There's no special direction. There's no special region or what have you. Obviously, there's big differences between here and the top of the pass right now. There's differences in the nearby, solar system and even close galaxies. But if you get to a sort of the equivalent of a 50,000-foot view of Earth is sort of a 200 megaparsec view of the universe. It's all the same. Looks like it's all the same stuff. There's no big difference one place or another. This strange contraption here was a sort of 1960s era radio telescope that two folks, Penzias and Wilson, were using, I think, to look at radio emissions from nearby galaxies. I don't know for sure, but one of the things they found when they did that was they were picking up a hiss, just sort of static noise everywhere they pointed it. They spent a lot of time worrying that the birds had sort of more or less done their business in the machine, and they cleaned all that out, and nevertheless, it still remained right there in all directions at all times. And that turns out to be a remnant of the early stages of the Big Bang. And that I'll mention a little bit more about that soon too. Also back in the 60s, Vera Rubin and Fred Zwicky combined observations of the rotation of a galaxy to realize that something was missing in what they were looking at. If you look at the picture of the galaxy there, forget that plot for the moment. Astronomers are able to actually tell how fast rotations are happening from the center of the galaxy. How fast are things going around out here and the like? They understanding gravity and all that, they expected to find that just like the way that the distant planets in our solar system travel much more slowly in the outskirts than the inner planets in their revolutions around the center. They were surprised to find that the distant objects out here in this galaxy didn't slow down the way they would have expected. The solution to that is that there must be a bunch of matter that we can't see. In fact, a lot of it, more or less 5 times more matter than the star, the shining stars there. It may be one of the new elementary particle. I'm going to talk about what we actually have in the list of what makes up the universe. It could be a new elementary particle. People have been looking for evidence of what that actually is for many, many decades. And so far, it's come up blank. So given that the galaxies are all moving farther apart and the furthest one are moving the fastest, yesterday we were all closer to one another than we are right now, or last year, a billion years ago, et cetera, et cetera. So people sort of walk that back to see where everything came from, since they know where everything is today and seems to be going. When you compress back everything, just like when you're kind of pumping a pump and filling up your bike tire, things heat up when it gets closer and closer together. The universe works the same way. And if you go back about 13 billion years, we have a universe that has extreme temperatures. Today, the universe is about, if you want to describe its temperature, it's about 2 or 3 degrees above absolute zero. 13 billion years ago, if you sort of imagine how everything gets shoved back into the beginning stages, we have a universe that had extreme temperatures, billions and billions and billions of degrees. And we have, with our accelerators and experiments, investigated not a universe worth of that, but sort of 1 or 2 or 10 particles at a time, with the energy that would be there in at that level of temperature. And our theories can actually point to even higher energies than we've looked at so far. And I'll talk a little bit about that too. I'm not used to talking as much as I am here, so. So again, the thing which I find interesting about all this is that the connections between elementary particles, which I'm going to talk about a little bit, in the entire cosmos. I was going to point to a periodic table, but I don't see one in here. But we all know about the periodic table of elements. There's 120 of them. If you look what goes into building those atoms, there are 17 fundamental elementary particles. And in fact, the periodic table itself is only these 2 quarks and an electron. The rest of these things play a role in the earliest instance in the universe, but they don't live long enough to even get past a minute or 2 of after what we'll call was the beginning of the whole thing at a Big Bang time. Most recently, this particle here, the Higgs, which is sort of helps give all these particles mass in one way or another, was discovered in this accelerator at the LHC in Switzerland. So these things are 10 to the minus 18th kilometers. The size of the universe is 10 to the 24th kilometers. You want to write that out, assuming I did my counting right. The universe is 1 followed by 42 zeros, as big as any of these little bitty particles are there. So here is mostly what the talk is. It's a complicated slide, but it is a history of the whole universe. So, so it goes. That's my excuse. From left to right, it starts back there in the region that is fuzzily called the Big Bang. But I want to make sure that nobody thinks that we know that there was a single point, an infinite this, or whatever. Nobody knows really what went on there close to that. I can talk a little bit more about that. But anyhow, it starts over there, goes from left to right. These intermediate, this envelope that's on here, it sort of describes the fact that the universe is getting bigger. And you notice there was 2 areas where it started to do that. It got bigger here, and it sort of went along for a while, and it's getting bigger again more recently. I'll talk about that down the road. So here we are today. We're here. It's spring of 2024, and you go backwards, and you notice the size changes. You notice that the temperature, along with that, the compression is happening. So everything in the universe is roaring around faster, faster and faster. The ingredients sort of change. Things start out in a roaring mess, and gradually structure starts forming, and the results from very different kinds of experiments actually inform this. And when I get through talking a little more about this, I'll show some of the experiments that are related to that. So this is the part I was just through telling you I wasn't going to talk about. At the various earliest moments, stuff happens that our theories can't quite deal with appropriately. There was an enormous expansion of the universe, even though it's been expanding, continuously for for 13 billion years and has even started to expand faster. There was an even relatively much bigger shot in the earliest moments of the universe, 1/1 followed by 30 zeros or something. So very, very rapid stuff. That's how some of the uniformity of the universe is thought to have been baked into the system. There's a cutoff, you know, I was seeing where people, how far back people are quasi bold enough to talk about how small it could get. In some places, people say that the calculations, at least, not the measurements, but the calculations show a universe that would probably fit inside of this room. It's unfortunately, we don't have any way to check if they're right or not just yet. But there's people trying. So by about 1 second from the beginning of things, the four different fundamental forces of nature, the strong interaction, the weak interaction, gravity and electromagnetism, separated from one another and started their merry way on and persist in that today. The universe is made up of fundamental particles, including quarks, electrons, photons, and neutrinos. Those, I showed you that little stack of things over there when I was talking about the periodic table. Those things were created by the energies, the high energy of that of the universe back then, and particle and antiparticle versions of each of those elementary particles were just were created out of the energy, and most of the matter and antimatter that got created in that, say you get a B and a B bar or something, a B and an anti-B, sooner or later they come back together and annihilate. We are in a universe where out of 1 billion of those pairs, for some reason or another, one matter particle survived that. That remains one of the key things. The question is, how come everything that got created in matter and antimatter pair didn't go back, and didn't we end up with, none of us here, nothing but a bunch of particles of light bouncing around? That is one of the key things, and there's all sorts of experiments that have been going on for a long time and that are continuing to go on. My first 20 or 30 years at the lab was related to how 1 or 2 of those elementary particles handled the matter and antimatter business. So the universe, you know, after a second is now continuing to expand, but it's expanding at you know, sort of a more sensible rate here. Protons and neutrons even began to form from some of the quarks. So that's the second in. 3 minutes after the Big Bang, things are cooled down enough so that these protons and neutrons sometimes start to come together to form what will be the nucleuses of atoms that have yet to form. The lightest elements, hydrogen, helium, and lithium, they appear in descending numbers, but in good proportions that that one would calculate for this business based on experiments that we've done in accelerators over the last 50 or 100 years, last 50 years. So one of the reasons that this whole thing seems to hold together and make sense is that we do know how these get formed, and because we can do experiments with them at sort of those temperatures. And in fact, when one looks out in the universe, one finds the right ratios of hydrogen, helium, and lithium laying around. The temperature of the universe at this point was still 1 billion degrees. And electrons were also roaring around, and they were still roaring around so fast that the positive nucleus couldn't catch them and trap them and keep them going around the thing. So we'd have to wait a little while longer. I think it's about 600,000 years, and 300, yeah, around 380,000 years after the Big Bang, those nuclei, the hydrogen and helium and lithium, they were able to actually capture some of the electrons that were zooming around and lassoed them. And at that moment, the universe, which was about the temperature of the surface of the sun, and just was the word's escaping me. It's a big plasma, which you couldn't see through at all. As those electrons started to get hooked up with their positive nuclei, the thing kind of cleared up, and photons that were around there were able to travel. Those photons that were picked up in that radio telescope had been, the last time they'd run into anything was 600,000 years after or 380,000 years after the Big Bang. It turns out, I can tell a bunch of us here had TVs with antennas and UHF channels and whatever. Channel 17, I think, 10% of the fuzz, if you turned your thing to channel 17, was the earliest scatters of from the Big Bang in the universe that hadn't landed anywhere for the last 13.25 billion years. So we've all had the detectors that we just didn't know it for a while. So about a billion years after, gravity starts, things are starting to cool down, gravity's starting to do its stuff, and the universe is starting to pull together and start to make stars and some early galaxies. And many of the stars that early on, I think, and I'm sure more of you guys know about the star sequences than I do, but they were big at the beginning, bright, and they flamed out really quick and started, forging higher atomic weight particles. 3 billion years after the Big Bang, the galaxies started to merge together in bigger and bigger ones, sometimes creating black holes in the middle and turning on, lighting up quasars that are extraordinarily interesting stuff. And supernova, which will show up, which I'll talk about in a minute, because they're key in mapping out the structure of where things are in the universe, how far away they are, and how fast they're moving. Supernova explosions started to be more populated and started blowing out heavier elements such as nickel, gold, silver, and even lead into the universe. Our sun didn't start forming until 8 billion years after the Big Bang. Sometime between that and about the time that our Earth started forming, this second rapid sort of universe expansion happened. To describe this, you can imagine having a ball that you throw up in the air. And you can throw the ball up in the air, and usually you throw it up and it always comes back down after a while and it slows down. If you threw it up with enough oomph, you could get it so it would always go up. It'd be slowing down, but it would always keep going up, and you'd never get it to the top. If you got that, if you tweaked it just that right, there's a sense in which the universe is kind of close to that. But the weird thing that was realized about 20 years ago now, and I'll show you some actual recent data showing this, is that we're in a universe where we throw the ball up, it starts slowing down, and all of a sudden it starts speeding up again and roaring away. That's what the universe is doing. And it doesn't bode well for how things are going to end, but that's not going to happen soon. So I want to talk about, I was talking about small stuff and big stuff. So that's the timeline of the universe. Now I want to talk a little bit about how we know what we think we know about small stuff. So the field of particle physics is to try to find out what is the smallest piece of stuff there is, and how does it behave. We look at, and in fact, in doing that, we end up sort of poking around at energies and temperatures that existed right at the time of the Big Bang. Viruses are, made up of bunches of molecules, which are made up of bunches of atoms, which have a smaller nucleus inside. A nucleus is made of protons and neutrons, and in fact, even protons and neutrons are made up of inner things. The question is, is there anything smaller than that? We don't know about that, but we continue to look for that kind of stuff. In order to see small things, you have to use light that has a wavelength much smaller than the thing you're trying to look at. This is just a picture of the electromagnetic spectra. So wavelengths of light, visible light. When we say light, we mostly think about visible light, and that's this little band up here, which is this sort of wavelength and this sort of frequency, and that lets us see things about like this. If you want to see smaller things, you need light with the smaller wavelengths, with higher energies, with higher frequencies, and that fact of nature means that it turns out our machines that we use to look at small things are among the biggest machines we have on the planet. The accelerator in Switzerland now is 300 meters underground, 300 feet underground, and it's in a circle that's about 15 or 20 miles around, in order to get the particles that are going to see this sort of stuff going fast enough, having high enough energy, so that they can actually see tiny things. The other thing, pointing out, we'll be talking about red shift and blue shift and whatever, and that all refers back to this little narrow slice of the electromagnetic spectrum that our eyeballs are sensitive to. Red being the lower energy and bigger wavelengths than the blue. This cosmic microwave background that started out way up here in the energy and has been sort of getting diluted in energy as the universe expands and it all cools down is over here in the microwave column. I think insects, a lot of insects see out here, so if you want to find out what is inside of something, you open it up. If you can't get it open, you bang it together and break it open. And that's the whole game with particle accelerators and atom smashers. In order to break them apart, you have to hit them with so much energy that it turns out, unlike breaking apart, say, a walnut, where the pieces that come out of the walnut are all each smaller than the walnut to start out with, Einstein's equation here means if you get particles going fast enough, you can make them, out of this can come particles that have more energy than the ones you're smashing, that have more mass than the ones you're smashing together. So here, conceptually, let's break a proton apart. We'll shoot a proton in from one end, or an antiproton and a proton from the other, from both sides, head-on collision, and out starts popping in specific ways, in specific directions, in specific combinations, those elementary particles that I was pointing to over on that side of the screen a while ago. And studying everything that we know, and studying, then even following up and studying sort of the W, or studying the B separately, that's what people do. What do they use to do that? Because they aren't sitting there with a magnifying glass looking at it. You have to invent, your own fantastic eyeball, which consists of a variety of different detector types that are sensitive to the different properties of each of those kind of things that came out, and also the directions that they came out, how far they go, what energy they were, and whatever. So shown here is one leg of a beam of protons coming in. This is the accelerator. This is the detector in the accelerator in Switzerland. Here's where the other come together. They slam together right here, and that artist's conception of stuff splatters around. All this data gets recorded. You know, there's 6,000 people that are a member of this particular experiment. They've been working for 10 years and continuing to refine and improve all these measurements. You can see sort of the size. There's somebody standing down there. This CMS stands for compact muon solenoid. There's a magnetic field in here. The C is compact. This is the smallest of the two detectors that they have in that machine. This is what it looks like in real life. They're about to, the interaction point is right here. They are about to slam the downstream end into the upstream end, fit it together. And this was this has been, I don't think it's been open since they put it in back in 2012. But do you get an idea of what those schematic things look like? So this is again that list. This is what comes out. There's just a few types of ingredients. Most of them have already effectively been dormant since the first seconds of the Big Bang. And these guys here, basically following the sort of constraints put on them by these force particles, are been what's been running the universe ever since. There is some reason to I don't think, but I think hope is also maybe a better word, that there's like one or two other particles. We would like to find a particle that maybe explains the dark matter. We would like to find a particle that's related to why the antimatter and matter didn't completely annihilate one another. And that's in the minds of going forward. So now I want to talk a little bit about the big stuff. I sprinkled this around 4 or 5 times in here because I wasn't sure where I wanted it, but do you remember where we did? So this is a picture in those different wavelengths of a galaxy, the same galaxy. This is the visible picture from that. Infrared, it looks like this. Radio waves, it looks like that. Ultraviolet looks like this, and X-rays look like that. This is for centuries. This is this is what we've learned. Even all these things. This is how we know what's going on out there. More recently, we started to get data from gravity waves, and also there is occasionally when the supernova goes off, one of the neutrinos, one of the elementary particles called the neutrino, also sends stuff out and signals, and we're building facilities to be prepared to see that. So Hubble said the universe is expanding. The people who are looking at rotations of galaxies, they can tell which direction and how fast the galaxy is rotating. They use something called the standard candle. There's a couple kinds of them, and I suspect you all know about that more than I do. But one of them is a particular type of supernova, and it is called the standard candle because I think it's about 1 1/4 or 1.4 times the mass of the sun. And if there's a nearby something other source of matter for this thing, part of this particular star's death plan is to a very rapid and very large explosion that is pretty consistent regardless of where it goes off. It's sort of like, you go to the store and you want to get a flare for the side of the road. You get a whole box of them. You can count on them all being the same brightness and whatever. That's what these supernovas are, and they are bright. This is one of them, seen back with the Hubble, I think back in 1994, and it is, in the brief period that it's fired up and shining at you, is as bright as the whole galaxy that it's a distant member of. And you wouldn't even think there's anything there compared to the stuff there. So it is very bright. So since these things are all kind of the same way wherever they go off, if they're near you, they're big and bright and in your face. If they're farther away, they're not as bright and they're smaller. On top of that, if you remember the Doppler shift and trains roaring at you and you hear the whistle blowing, and as it comes, it's higher pitch and it goes by and it's lower pitch, light does the same thing. So if this particular supernova is moving towards us, when it goes there, the higher pitch, if you will, is effectively a higher energy, is a bluer light than it would be if it wasn't. And if it's going the other way, away from you, it's redder. And that's what redshift is. And so you put all that stuff together and you see, you can see where something is and which way it's headed from there. This is another way of saying that. Judy and I talked about this last night for long enough to decide that I'm not going to talk about this particular view anymore. However, you know, there's one, they're the same kind of things. There, it's up there, it's smaller and farther away. It's running that way, so it's redder. This is closer, so it's bigger, and it's going that way, and it's bluer. So, but no, I'm wrong. It's also redder, but redder is green in this case. It's that's why I wasn't going to show that, but I did anyway. So at Fermilab, we built a camera to measure the expansion of the universe. This is a picture of one of the lenses for that camera that was built, and different filters slide in front of it as you take a picture with this filter, and you take another picture with the next filter, etc. It is 580 megapixels of CCDs. The thing is about this big, the central circle, and it was installed in the Ceratololo observatory. It's in the Chilean Andes in South America. It's high up, it's dry, it's perfect. You got some other observatories in the general area, and it's just a beautiful place. I've not been there, but people who have worked in that, it's as pretty as this said it is. Here's that camera installed on the telescope. The camera is up here. Everything comes in and reflects back off onto the sweet spot of the camera. Again, this is the camera, so that thing is about that big. This is hot off the press. This was just released in January of 2024. This instrument was used to measure, I think there's 2,000 supernova plots in here. Let me show you what this is. So they observed 2,000 of those supernovas that I saw over the last year. Each one of them is plotted on here. You can look up here. You can see the scale is supernova distances here. So this is it's real bright, it's real dim. You know, farther away, it's real red, or it's not so red. And so each of these supernova gets plotted on here. You see two curves, the green one that fits the data, and the blue one is the prediction if the universe was still just, if you're just throwing the ball up and the ball hasn't decided to go faster. The fact that the green and the blue don't meet was first shown on different scales and not with so much data or whatever back in the just at the turn of the century, and the folks who did that got a Nobel Prize for that. Red Lodge was lucky because last year there were two talks in town about the James Webb Space Telescope. There's a person down there that went up. It's actually sitting, again, as I'm sure you know better than I do, it's sort of sitting on the dark side of the Earth, sort of hiding from the sun as it tries to take advantage of the infrared sensitivity of the camera. Here's a a picture that came out in the first days of turning this thing on, right? And, you know, if you had a black piece of paper and took a paper clip and punched a hole in it and held it at arm's length and looked through it, that's what you'd see here. That's what's out there in the dark. And you can see all sorts of features that are worth learning about sometime or other. The way that some of these images of galaxies are warped and whatever the gravitational objects between the thing that is making the thing and the thing sort of warp it. But don't have time for that today. Here, I think this is Hubble, but this is what you see with visible light. But if you want to look a little redder and see a little bit of the richer galaxies, it's the same shot with the background. So there's a lot going on out there for sure. Okay, so that was a picture of the teeniest thing you could look at. This is now a picture of everything. This is the cosmic microwave background radiation, and you think of yourself as inside and looking in all directions. So it's like it's a version. It's like taking the Earth and flopping it and putting it on a flat map. The things you should look about here is pretty much a couple things. First, kind of looks the same everywhere. On the other hand, it's also a little different here and there. In some places, it's even a little bit more different. All of the little dots here, the sizes of these smallest little appearing dots here are consistent with a certain amount of dark matter in the universe, and consistent with the rapid expansion and explosion and then cooling over the time when this picture was. So the light that hit the instrument that ended up contributing to the plot at this particular point left at 380,000 years after the Big Bang, and it hadn't hit anything since then. The red are areas where there's a slight excess of stuff compared to the overall smoothness of it, and the blue where there's a slight deficit. You can use the detector that I just showed you that did the measurement of the dark energy to look in this region of space and see if it sees a deficit of stuff today and since see if there were fewer galaxies there today than it looked like there was going to be back there when the baby picture was taken at 380,000 years, and in fact it is. The next, this is an instrument that is so sensitive that it could look this way because that's the instrument resolution was the limiting factor. In fact, the instrument could resolve even smaller features on here than this. So these are real features. That's the real size of it. This particular result came from a European satellite, the Planck satellite. We don't need to do that anymore for at least for another couple of generations or whatever. What we do need to do to learn more about it is look at the polarization inside these little teeny dots and see the difference between the ones in the red and the ones in the blue and the neighboring ones and whatever, the actual polarization of the light that comes out. And there's several efforts underway to do that. And I'm almost at the end here. So again, last night, this was going to be 2 hours if it wasn't for. So again, this is the right half of what I just showed you back in '92. And this was another Nobel winner. This was the resolution. That's what you knew back then. There was an improvement there, but it still wasn't good enough to see the fine thing. This one could have, as I said, could see smaller features on it than it does. And so we don't need to build another one for a while, at least. Here's a group that going to the South Pole. They're actually been there for a few years on and off, and they are going to measure that polarization. And I show you a picture of them here. See this weird looking thing? That's the same weird looking thing, sort of like the first one that the guy in mid 1960s. all that, so that's how the eyeball looks. This is the retina that gets inserted at the focal plane of this. And they are looking for that polarization in the hopes of learning something about that first rapid inflation expansion at 10 to the minus 30 seconds. So they travel that way. This is what scientists look like. They don't look like this. They look like this. So this was the winter crew that goes there in the summer. And they were installing this on the telescope there, just right at the South Pole. It's great there because there's no water in the air, and microwaves, they're trying to measure microwaves, and microwaves just get eaten by water, which is why our microwaves work when we want to warm things up. The water jiggles right at so this is what the universe is made of. So all the stuff I've been talking about, the ordinary stuff, it's up here. It's a whopping 5% of what's out in the universe. In fact, most of the ordinary matter in the universe is dust, which is just floating around in between galaxies and the like. The dark matter that explains why these galaxies sort of rotate the way they do, that's 25% of the energy in the universe. And this more recent dark energy where the ball's starting to zoom up away from us and not slow down anymore is 70%. So here's the unknowns. I referred to them a couple of times during this thing. We don't know what really went on at the earliest, teeniest instance. We don't know why matter and antimatter didn't completely annihilate. We would have not ended up, but there wouldn't have been nothing. Dark matter, is it maybe a new particle that's discoverable with the next generations of various searches that's going on? Dark energy could be just a constant in Einstein's general theory of relativity, and that we could know that the constant is minus 1/3 or whatever it is, or maybe there's something more dynamic going on. We don't know. You got to study it more and more. Our theories of gravity and quantum mechanics don't work at the earliest instance. And it doesn't mean that the universe was infinite in energy and zero width and size. It just means we can't trust our theories down that far. So we may be able with more studies of neutrinos or gravity waves or other things to find out more about that. And just as a heads up as to what Fermilab is going to do next, one of those small particles, the neutrino, is maybe a candidate for playing a role in why matter and antimatter asymmetry wasn't perfect, and we ended up with a little bit of matter in a lucky universe as a result of that. The experiment, here's a picture of Fermilab. We're going to make a beam out of that near accelerator tunnel, the one that was in the foreground, and shoot it up and bend it down and send a beam of neutrinos through the Earth to Leeds, South Dakota, in the old Homestake mine, where they did a lot of studies of the solar neutrino problem for years. This is a expensive, big deal going on. It's under construction now. The excavation is done there, and we've done this process before, sending a beam from Fermilab, pointing it a little bit north and going to Minnesota in another mine. This is going to be the one to end all neutrino experiments, and it should be coming online at the end of this decade if everything goes according to plan. So in summary, the inner space and outer space are connected, and they really sort of reveal the history of the universe. There's very few laws and very few kinds of ingredients for all the wild differences, not only in space, but life and all that stuff comes out of the same old stuff. we're always improving microscopes and telescopes of one sort or another to expand these visions. I didn't say much about it, but all of these are international collaborations. We go some places to do experiments where they have the facilities and everybody comes to us. In the early days, we had Soviet scientists living on the site for years at a time. And that sort of, we're persisting now, although the world situation is getting a little dicey, making that awful hard for the people, especially in Europe. And so I think I'll just say thank you. It's a lot of fun. Although I'm ready to retire.
Greg, can we take some questions?
Sure.
Maybe there.
If anybody
Audience here, or there might be somebody online.
online or, now or some other time or whatever.
I'm curious about what you're most excited about, given like the pace of how quickly we're learning and expanding our knowledge in these fields. Like, what are you most excited about?
Well,
that you think is coming?
What you usually get excited about is the next thing that's actually finally built and about to turn on. And so there's upgrades to that thing in Switzerland that are going to push further and further. On the other hand, that was going to be the thing that was going to show us supersymmetry during the first year back in 2012. We don't see any sign of that. There's a whole bunch of smaller activities looking for these dark matter particles, and they often are underground. And I gave a talk to Kurt Nell's class about 4 or 5 years ago where I told them, we have this new experiment coming online. There's good reason to think we're going to see something, and okay, it ain't there. Okay, it ain't there. In fact, what they thought was what everybody felt was what it was going to be. It has now been looked at by a bunch of different experiments, and it's at least not there at the level it was supposed to. And people are now realizing that this could be almost anything now. And so you got to design all sorts of new detectors to pull it off. All of this stuff is not cheap, or none of this stuff is cheap, or whatever the right way to say that is. And so, thanks for coming.
I don't see any questions online, but I just kind of wondered with JWST and the discovery of the larger galaxies closer to the Big Bang, how does that fit into all of it?
I don't know the details of that. I did look in, a lot of time here's another similar thing. So I don't know if there was somebody who said, gee, we've seen a star and it's 15 billion years old. Okay. And so how can that be in a 14 billion year old universe? And as people looked further and further, they realized that the error bar on that 15 billion years was a little bigger than they thought first, and they didn't do it. I would say the best thing to do is to let the JWST really crank out and work for it, get its 5 or 10 years worth of data, and it'll clear that all up. And it may be that, just like this old star that was too old to be true, things sort of readjust on there. I mean, this field it's tough. 40 years ago, none of these predictions, you couldn't make any of these predictions with any degree of confidence. There used to be a joke by the people that like me, that worked in particle physics at the small end of the scale, and we would talk about the cosmologists, and we would say, they're never in doubt, but they're often wrong. Okay, and so so it all. It's getting better, and the simple fact is, and that's what makes trying to decide how to fund these things, is we don't know. It could be a small experiment in the bottom of some mine that some a small number of people are working on that'll pull this off. Or it could be when this new neutrino thing that costs quite a bit of money, in the billions, is on and running, comes out with its first data. You just don't know.
There's one question online, Brad Burdick is asking, do you know what MSU Bozeman is currently working on in regard to gravitational waves?
No, I don't. I know that there's a big group there that's working on quantum information science and whatever, but I don't know. In fact, I don't know much about gravity waves, and Fermilab's involvement in that is mostly to when the gravity wave detectors say, hey, something happened over there in the universe, they are able to aim their stuff, their electromagnetic telescopes and the like at there and sort of look at it.
Any other questions for Brad? Well, thank you so much, Brad.
Thank you. Thanks. Thank you all.
No.